Let's talk about ice. You've walked on it. You've slipped on it. Maybe you've fallen flat on your back on a frozen sidewalk in January. You've watched hockey players glide across a rink at impossible speeds. You've seen figure skaters spin like they're defying friction itself. So ice is slippery, obviously. You know this from direct experience. You must understand why, right? Okay, explain it to me. Why is ice slippery? And don't just say because it's smooth, because glass is smooth and you can walk on glass just fine. Don't say because it's cold, because a frozen metal pole isn't particularly slippery. There's something specific about ice, something about water in its solid form that makes it behave differently than almost any other solid substance on Earth. Most people, when pushed, will mumble something about melting or pressure or a thin layer of water, and they're not completely wrong, but they're not right either, not really. Because the real answer, it took scientists over a century to figure out, and what they discovered changes how you should think about solids themselves. Here's what you probably think happens. You step on ice. Your weight creates pressure. That pressure lowers the melting point of the ice directly under your foot. The ice melts into a thin film of water. You slip on that water. Then when you lift your foot, the pressure releases and the water refreezes. Simple, elegant, satisfying. There's just one problem. It's wrong. Well, not completely wrong, but mostly wrong. And here's how I know you should be suspicious of this explanation. Try this thought experiment with me. Take an ice cube out of your freezer. It's negative 15 degrees Celsius. Place it on your kitchen counter. Now, very gently, touch the top of it with one finger. Barely any pressure at all. Is it slippery? Yes. Incredibly slippery. Your finger slides right across the surface with almost no friction, but you're not applying nearly enough pressure to melt ice at negative 15 degrees. Not even close. You'd need thousands of pounds per square inch to lower the melting point that much. Your finger is applying what? Maybe a few pounds per square inch at most? So why is it slippery? Or here's another one. Why can you ice skate at negative 40 degrees Celsius? People do. In places like Alaska and northern Canada, outdoor rinks operate in brutal cold. The pressure from a skate blade cannot melt ice at negative 40. The physics doesn't work, but the slipperiness remains. So what's actually happening? Before we can understand why ice is slippery, we need to break down what we're actually asking. What does slippery even mean? Physically, we're talking about friction, or rather, the lack of it. Friction is the force that resists motion between two surfaces in contact. When you walk on concrete, there's high friction between your shoe and the ground. That friction is what allows you to push backward and move forward. Without it, your foot just slides. No grip, no traction, no control. That's what happens on ice. The coefficient of friction, the number that tells us how much grip exists between two surfaces, is incredibly low for ice. It's around 0.02 to 0.05, depending on temperature. For comparison, rubber on dry concrete is around 0.7 to 1.0. Ice has almost no friction. But why? What is it about the molecular structure of ice that eliminates friction? Here's where we need to think more carefully. Ice is a crystalline solid. The water molecules are locked into a rigid lattice structure, hexagonal, beautiful, highly ordered. Each molecule is hydrogen bonded to 4 neighbors in a tetrahedral arrangement. This is not a soft substance. Ice is hard. You can build buildings on it, drive trucks across frozen lakes. It has structural integrity. So when you press something against ice, you're pressing against a solid crystalline structure. 2 solids in contact should have decent friction. The microscopic roughness of each surface should interlock, but they don't. Not with ice. Your shoe or skate blade just glides across as if the surface were coated with something. And that's the key insight, the surface, not the bulk. We're not asking why ice as a whole is slippery. We're asking why the surface of ice behaves differently than we'd expect from a normal solid. Because here's the thing about surfaces. They're weird. The molecules at the surface of any material are in a different environment than the molecules in the interior. In the bulk, every molecule is surrounded by neighbors, fully bonded, stable. But at the surface, those molecules have neighbors on one side and nothing but air on the other. They're incomplete, unsatisfied, and that changes everything. So let's talk about what happens at the surface of ice. Imagine you're a water molecule trapped in the ice lattice. In the interior, you're hydrogen bonded to 4 other water molecules. 2 above, 2 below in a tetrahedral arrangement. You're locked in place. You can vibrate a little, but you can't move. You're part of a rigid structure. Now imagine you're a water molecule at the very surface. You've still got neighbors below you and to your sides. But above you, nothing, just air, just empty space. You're only bonded to 2 or 3 neighbors instead of 4. You have unsatisfied hydrogen bonds, dangling bonds. And this creates a problem, energy. Those dangling bonds represent excess energy. The system is in a higher energy state than it wants to be. Nature hates excess energy. Systems always try to minimize their energy. So what can the surface molecules do? They can't form bonds with air. There's nothing to bond to. They can't easily rearrange into a different crystal structure. The bulk ice below them is holding them in place. But they can do something. They can become more mobile, more liquid-like. Here's what happens. The surface molecules, lacking full bonding constraints, start to vibrate more. They become disordered. They form and break hydrogen bonds rapidly with their neighbors. They're not quite liquid. They're not quite solid. They exist in a quasi-liquid state, a thin layer, just a few molecules thick, that has liquid-like properties, even though the temperature is well below the freezing point. This isn't melting. Melting happens when you add heat energy and break apart the crystal lattice throughout the bulk material. This is a surface phenomenon. The surface is inherently disordered because the molecules there exist in an incomplete bonding environment. And this quasi-liquid layer, it's been measured. Scientists have used techniques like infrared spectroscopy and some frequency generation spectroscopy to probe the molecular structure of ice surfaces. What they find is that even at -10, -20, -30 degrees Celsius, there's a layer of disordered, mobile water molecules on the surface. The thickness varies with temperature. Warmer ice near 0 degrees has a thicker layer, maybe tens of nanometers. Colder ice has a thinner layer, maybe just 1 or 2 nanometers. But it's always there, always present. This is called the quasi-liquid layer, or sometimes the pre-melted layer. And it's not unique to ice. Many crystalline materials have disordered surface layers. But ice is special because water's hydrogen bonding network is so specific and directional. The surface disorder is particularly pronounced. And this quasi-liquid layer is what makes ice slippery. You're not sliding on solid ice. You're sliding on a nanometer-thin film of quasi-liquid water that exists at the surface. It acts as a lubricant. A molecular scale layer of mobile molecules that can flow and rearrange, eliminating friction between your shoe or skate and the solid ice beneath. Now you might be thinking, okay, that's interesting, but a layer that's only a few nanometers thick? How can something so thin create such dramatic slipperiness? Good question. Let's think about what friction actually requires at the molecular level. When 2 surfaces are in contact, friction comes from interactions between the molecules of each surface. Chemical bonds forming and breaking, mechanical interlocking of rough features, adhesive forces. For friction to exist, the surfaces need to stick together, even momentarily. They need to resist sliding past each other. On a normal solid surface, this happens. When your rubber shoe presses against concrete, the molecules at the interface interact. The rubber deforms slightly, conforming to the microscopic roughness of the concrete. Chemical interactions create temporary adhesion. When you try to slide, you have to overcome these interactions. That's friction. But with ice, the quasi-liquid layer changes everything. Instead of your shoe pressing directly against the crystalline ice surface, it's pressing against a layer of mobile, liquid-like molecules. Those molecules can flow, they can rearrange, they can slide past each other with minimal resistance. It's like the difference between dragging your hand across sandpaper versus dragging it through a thin film of oil. The oil allows motion because the molecules within the liquid can move past each other. They're not locked in place. The quasi-liquid layer on ice does the same thing. And here's the beautiful part. The layer doesn't need to be thick. In lubrication science, there's a concept called boundary lubrication. When you have 2 surfaces separated by an extremely thin layer of lubricant, just a few molecules thick, it can still dramatically reduce friction. The lubricant molecules act as molecular ball bearings. They're mobile. They can rotate and slide and rearrange. They prevent direct solid-to-solid contact, and that's sufficient. The quasi-liquid layer on ice is the ultimate boundary lubricant. It's always there. It's self-generating. The surface itself creates it through the thermodynamic necessity of minimizing energy. You don't need to add anything. You don't need to melt the ice. The ice surface is inherently slippery because of its molecular structure. Now, does pressure play a role? Yes, but not the way most people think. When you press hard on ice, with a skate blade, for example, you can generate frictional heating. The motion of the blade sliding across the surface creates heat. That heat can thicken the quasi-liquid layer slightly, making it even more slippery. And under extreme pressure, you can induce localized melting. But this is a secondary effect. The primary reason ice is slippery is the quasi-liquid layer that exists regardless of pressure. You can prove this by gently touching ice. Minimal pressure, no heating, still slippery. The surface itself is the answer. Let's make this even more concrete. Why does the slipperiness of ice change with temperature? If you've ever walked on ice in the dead of winter, you might have noticed that extremely cold ice is actually less slippery than ice near the freezing point. At negative 30 degrees Celsius, you have more traction than at negative 5 degrees. Why? Because the thickness of the quasi-liquid layer depends on temperature. Temperature is just molecular motion. Higher temperature means molecules vibrate more energetically. At temperatures close to the melting point, the surface molecules of ice are vibrating quite a lot. They have enough thermal energy to break hydrogen bonds frequently and exist in a highly disordered state. The quasi-liquid layer is thick, maybe 10 or 20 nanometers, very slippery. As the temperature drops, the molecules have less thermal energy. They vibrate less. The quasi-liquid layer becomes thinner. At negative 30 degrees, it might be only 1 or 2 nanometers thick, still present, still creating some lubrication, but less pronounced. More of the surface molecules are locked into the crystal structure. Friction increases. You have more grip. This is why ice skating is actually more difficult on very cold ice. Professional ice rinks are typically maintained at around negative 5 to negative 7 degrees Celsius. Cold enough to keep the ice solid and hard, but warm enough to maintain a thick quasi-liquid layer for optimal glide. Too cold, and the skaters complain about poor ice. Too warm, and the ice becomes soft and the blade digs in. There's a sweet spot, and it's determined by the physics of the surface layer. Now here's another interesting aspect. Different types of ice have different slipperiness. Ice formed from pure water is different from ice formed from water with impurities or dissolved gases. Why? Because impurities affect the crystal structure and the surface energy, they can disrupt the formation of the quasi-liquid layer. Salt, for example, when incorporated into ice, lowers the freezing point and creates defects in the crystal lattice. Those defects change the surface properties. This is one reason why salting icy sidewalks works. Yes, salt lowers the melting point and helps melt the ice, but it also disrupts the smooth quasi-liquid layer, increasing friction even before complete melting occurs. The microscopic physics of surfaces matters. And here's one more mind-bending aspect. The quasi-liquid layer isn't perfectly uniform. It has structure. Recent computational studies using molecular dynamics simulations show that the layer has regions of higher and lower density, fluctuating patterns of hydrogen bonding, dynamic heterogeneity. It's not just a simple liquid film. It's a complex interfacial region where order and disorder coexist, where solid and liquid blur together. This is the frontier of condensed matter physics, understanding how molecules behave at interfaces, how surfaces differ from bulk, how the nanoscale world creates the macroscale properties we experience. And ice, this common everyday substance, is one of the most fascinating examples we have. You walk on it, you slip on it, and underneath, at the molecular level, is a beautiful, complex dance happening. So here's what should blow your mind. Ice isn't slippery because we do something to it. It's slippery because of what it is. The surface of ice exists in a fundamentally different state than the interior. Not because of pressure, not because of heat, but because surfaces themselves are different. This is true for all materials. Every solid you've ever touched has a surface layer that behaves differently than the bulk. The molecules there are in an incomplete bonding environment. They're higher in energy. They're more reactive, more mobile, more disordered. We just don't notice it most of the time because the effect is subtle. But with ice, because of water's unique hydrogen bonding and because the quasi-liquid layer creates such low friction, the effect is impossible to ignore. You experience quantum mechanics and statistical thermodynamics every time you slip on a frozen puddle. Think about that. The reason you fall on your butt in the winter is because water molecules at a surface have dangling hydrogen bonds that create a thermodynamically unfavorable energy state that the system minimizes by increasing molecular disorder in a nanometer-thin interfacial region. That's the real explanation. And nobody figured this out until the late 20th century. Scientists argued about why ice is slippery for over 100 years. Pressure melting was proposed in the 1860s. It was taught in textbooks as fact. It took advanced spectroscopy techniques and computational molecular dynamics in the 1990s and 2000s to finally prove what was really happening, the quasi-liquid layer, the surface phenomenon. Feynman would have loved this. A simple question, an obvious everyday experience, and underneath a beautiful, subtle, complex answer that reveals deep truths about how nature works at the smallest scales. So the next time you walk carefully across an icy parking lot, pay attention. You're not just avoiding a fall, you're experiencing one of nature's most elegant surface phenomena. You're interacting with a material that exists simultaneously as solid and liquid, a boundary between phases, a place where the rules are different. And here's the deeper lesson. The world is not what it seems on the surface, literally. Every material, every substance, every interface has hidden complexity. What appears simple, ice is slippery, turns out to require sophisticated physics to explain properly. What seems obvious, pressure melts the ice, turns out to be mostly wrong. The truth is weirder and more beautiful than the simple story. And that's how nature works. The closer you look, the more interesting it gets. The more you question, the more you discover. You think you understand something? Explain it. Break it down. Ask why at every level. And be prepared to be surprised. Because the universe doesn't owe you simple answers. But it does offer, if you're willing to look carefully, endlessly fascinating ones. That's physics. That's the joy of understanding. Now go slip on some ice and appreciate what's really happening.